Hey, what up, guys? My name is Juan. I'm a student at the Benemérita Universidad Autónoma de Puebla, and today in this video I'm going to be talking about separable and non-separable differential equations and how to identify them. To begin with the presentation, we're going to be giving an introduction to the separable and non-separable differential equations. Here we're going to be learning the definition and how to tell them apart from other types of differential equations. And also what makes we're going to be learning what makes a separable differential equation separable. Then we're going to be solving an example of a separable equation, and then we're going to be learning this very useful method that will help us know if a differential equation is separable or not without actually having to solve the equation itself. Then we are going to be solving a second example using this method, and at the end we're going to be giving a summary with all the concepts and rules learned in this video. Separable differential equations. What do we understand for a separable differential equation? Supposing that we have a differential equation written in this form, which is that the derivative of y with respect of x is equal to a function g of x multiplied by a function h of y. And in this expression, as long as the function h is different to 0, the terms can be rearranged to obtain this expression right here, so that each variable of the equation is separated. So in this expression we can see that each term of each variable of the equation is grouped in one side in opposite sides of the equation. Here in the left side we have all the terms with y, and in the right side we have all the terms that depends of x. Well, now knowing this, we can say that a separable differential equation is a type of differential equation which variables can be grouped along with their respective derivative in opposite sides of the equation. Well, but now that we know the definition of a separable differential equation, uh, how do we tell them apart from a non-separable differential equation? Well, there are actually two methods that I know, which I'm going to be explaining in this video, of how to tell apart a separable differential equation from a non-separable differential equation. The first method is actually the longest, and it's more of a trial and error kind of method, which consists in just going straight to solve the equation. And if it can be separated, well, it's a separable differential equation, and if not, it's not a separable differential equation. That's it. Okay, in order to solve this kind of equations separable, uh, we're going to be using this method known as the variable separation method, which only works with functions written in this form, and only works when the function f of x and y can be written as a product. We actually need to remember this in order to being able to solve the first example that we're going to be explaining. So for this first example we have this differential equation, but after we get to actually solve the equation, we need to remember these tips, these points that will help us to solve the equation more rapidly and easily. Okay, we always need to remember that the equation will be solved by y, and all the constants and other terms will be grouped in the x side of the equation. Then we also need to remember that in order to solve this equation, it needs to be written in certain kind of form. Okay, but we mentioned the form that the equation needs to have in order to be solved by this method. So how do we get there? Okay, we have this equation, which is the derivative of y with respect of x plus 2xy, and all of that is equal to 0. We need to clear the derivative of y with respect of x in order to get this expression in the right form. So what we do is we take the 2xy and pass it to the other side of the equation with a negative sign, like this. So we will end up with a derivative which is equal to a multivariable function written as a product. So now that we have this expression written like this, we can continue to solve the equation. So what we want to do next is to get all of the variables, all the terms that depends on y in one side of the equation, and all the terms that depends on the variable x on the other side of the equation. So what we do is that we take these differentials as normal variables so that we can move them throughout the equation. So what we did here was that we take the differential of x as a division and pass it to the other side of the equation multiplying. Now we have the differential of y that's equal to minus 2xy differential multiplied by differential of x. But we have this y, this variable, in the wrong side of the equation. So what we do is with that, as it is multiplying, we pass it to the other side as a division. So we end up with these expressions, with this expression that is simplified this way. So now that we have all of our variables in each side of the equation, what do we do next? Well, we need to remember that we have the dy and the dx are differentials. And how can we cancel out this differential? How can we eliminate them? Well, that's easy. We just integrate both sides of the equation, so we end up with an expression like this. Uh, so the integrals, what are going to do is to cancel out the differentials. Sorry, I made a mistake here. Are going to cancel out with the differentials, and we're going to end up with a whole new expression, but without differentials, only with the variables, which we will then will have to clear in order to get the result of the equation. So we proceed to integrate. Okay, I believe we all know that the integral of dy over y is equal to the natural logarithm of y, which is equal to the 2 minus 2x squared over 2 plus c1, which is our constant. But right here we can simplify this expression just by eliminating these 2's that are multiplying and dividing, and we will end up with this expression. So we have that the natural logarithm of y is equal to minus x squared plus c1. What we do next, well, in order to solve this equation we need to get the values of y. So how do we do that? How do we take the y out of the natural logarithm? Well, we just applied Euler to both sides of the equation. So we end up with this expression. Okay, we have this expression, and there's this rule that says that when a natural logarithm is elevated as an exponent of the Euler number, the Euler and the natural logarithm will cancel out. The result will be just the expression inside the natural logarithm. In this case is y. So by doing that we get this expression which says that y is equal to e to the minus x squared multiplied by e to the c1. This c1 was obtained just by decomposing the expression above into two different uh, expressions by the simple rule of exponents. Okay, we did this in order to convert this e to the c1 into a constant. This is possible because e is a constant and c1 is also a constant, and a constant elevated to a constant is equal to another constant. So this expression will be transformed into y that's equal to c, this expression over here, multiplied by e to the minus x squared. So we get this. We get this, and this will be the resolution of our differential equation using the variable separation method. So by solving this example, we get that this equation was indeed separable. Why? Because the terms were able to separate into different sides of the equation. But in order to get this conclusion, we had to resolve all the equation. And well, this was just a simple example, not very complex, actually, not complex at all, just a pretty basic example. But there are another equations that require a more complex approach in order to tell if they are separable or not, and that approach is the method that we're going to be explaining in the next slides of this presentation. Now we're going to be explaining the general method of how to know if an equation is separable without actually having to solve the equation to know if it is indeed separable or not. We will start by having a differential equation of the form dy over dx that's equal to a multivariable function f. From that expression, from that differential equation, we're going to take the function, the multivariable function f, and propose values for both x and y, so that when we substitute those values into the function, the result must be different from 0. Now we calculate the value f of x0, y and y0 and save the value. Then we will need to find the expressions for f of x0, y and fx, y0 and prove if this expression right here is true or not. If the expression is true, the equation will be separable. But if the expression is not true, the equation won't be separable. So right now we're going to be explaining this method using an example. Here we have the equation that we're going to prove if it's separable or not. Okay, what we need to do first is to take this part of the equation, which is the multivariable function f, and then we will need to propose values for both x and y. Now that we x and y, we can substitute them into the f function. It's this, and calculate the result of this substitution, which in this case is equal to 3. We will save that number for later, and then we will proceed to calculate to calculate the values of the multivariable function evaluated in y and in x, so that we can get these expressions right here. After doing that, and also having this value, we will then proceed to prove if this expression is true. So we need to substitute all of these values into this equation. Well, yes, this equation, and solving it to know if this differential equation is separable or not. So we proceed to substitute all the values, and we will get this expression. Then we expand this expression to see if we can eliminate or cancel out some common terms, but after analyzing the expression, we can tell that this expression is not equal to this other expression. So this tells us that the differential equation that we have at the beginning, it's not separable and will need another method to be solved. Here we have the expression that says that it is indeed not separable.